Welcome to this explainer. Today, we're going to look at a singular, really elegant rule of physical chemistry that is secretly running our daily lives, while simultaneously dictating the absolute extremes of human survival. We are demystifying Henry's Law. It's this fascinating scientific journey that takes us from the fizzy bubbles in your everyday drinking glass, all the way down to the crushing depths of the ocean floor, and then straight up into the thin, unforgiving air at the very edge of space.
So, I want you to start by thinking about a really curious, almost absurd question. What does a simple, fizzing carbonated beverage have in common with a fighter pilot flying a high-performance jet tens of thousands of feet in the air? I mean, on the surface, absolutely nothing, right? But physiologically and physically, they are governed by the exact same scientific principle. The mechanics of what happens when you crack open a fresh sealed bottle of your favorite carbonated drink are the exact same mechanics that constantly threaten a pilot flying at extreme altitudes without a pressurized cabin.
Okay, let's dive into this. Here is our roadmap for today's explainer. We'll start with the soda bottle science, define Henry's Law, look at diving in aerospace medicine, cover treating decompression sickness, and finally wrap up with temperature and other variables.
Section 1. The soda bottle science. The physics of the fizz.
Let's ground this heavy science in something we've literally all experienced before we get to the law itself. To understand the physics here, we first need to understand solubility. Basically, solubility is defined as the maximum amount of a solute, which in this case is a gas like carbon dioxide, that can be dissolved in a specified amount of solvent, like water, at a constant temperature. Now, what's really interesting here is that solubility isn't just some fixed magical number that never changes. It's highly dynamic. It depends heavily on the specific nature of the gas, the chemical makeup of the liquid, the ambient temperature, and, most importantly for our journey today, the ambient pressure pushing down on that liquid.
Section 2. Defining Henry's Law. The core science.
Let's meet the English physician who figured all of this out back in 1803, William Henry. Henry's law states that the amount of dissolved gas in a liquid is directly proportional to its partial pressure above the liquid at equilibrium. Okay, let's translate that out of textbook speak and into the real world. Think of a sealed, highly pressurized bottle of a carbonated beverage. The tiny space right above the liquid inside that bottle is packed with high-pressure carbon dioxide gas. And because that pressure is so incredibly high, a massive amount of carbon dioxide is forced to dissolve perfectly into the liquid itself, which maintains equilibrium. But the moment you twist off that cap, you hear that deeply familiar hiss. The gas pressure above the liquid drops precipitously to match the normal, much lower atmospheric pressure of the room you're in. Because the pressure above drops, the maximum amount of gas the liquid can effectively hold also plummets. So what does that trapped gas do? It violently escapes the solution in the form of rapidly expanding bubbles and foam.
And this beautifully illustrates the formulaic version of Henry's Law. P1 over A1 equals P2 over A2. In this equation, P stands for the partial pressure of the gas, and A stands for the amount of gas dissolved in the solution. It is a remarkably simple, brilliant ratio. It mathematically proves that any change in pressure results in a perfectly proportional change in the dissolved gas. If the pressure goes down, the amount of dissolved gas absolutely must proportionately go down. That extra gas has to go somewhere, so it forms those bubbles. Keep this exact formula in your mind, because it is about to become a very literal matter of life and death.
Section 3. Diving and aerospace medicine. High stakes physiology.
We are now taking this science completely out of the beverage aisle and injecting it directly into the human bloodstream. See, our blood is essentially just a liquid solution carrying dissolved gases, operating exactly like the water in our beverage. When scuba diving deep underwater, a diver breathes air at an incredibly high ambient pressure simply because the sheer weight of the ocean is physically compressing them. According to Henry's Law, this immense pressure forces excess gas, particularly metabolically inert nitrogen, which our bodies don't even use for energy, to dissolve deep into their blood and tissues. If that diver ascends to the surface too quickly, the surrounding water pressure drops sharply. Suddenly, that supersaturated nitrogen has nowhere to go, so it turns into tiny, dangerous bubbles directly inside the bloodstream. Conversely, in aerospace medicine, the mechanism is completely reversed, but the physiological outcome is the exact same. As a pilot ascends high into the atmosphere, the ambient atmospheric pressure drops way below normal sea level equilibrium. Even without breathing pressurized air beforehand, the sudden, dramatic drop in pressure at high altitudes means the human bloodstream can no longer hold its normal, everyday amount of dissolved nitrogen. And, you guessed it, bubbles form once again. Whether you're coming up from the crushing deep ocean or flying rapidly up to the edge of space, dropping the ambient pressure essentially turns your bloodstream into a newly opened soda bottle.
So a perfectly logical question arises.
How do millions of us fly in commercial airplanes every single day without our blood bubbling over? The answer is 8,000. Specifically, 8,000 feet. Commercial airliners are designed to continuously pump conditioned air into the sealed cabin to maintain an artificial ambient pressure. Even when the plane is cruising at a staggering 35,000 feet, the pressure inside the cabin is maintained at an equivalent altitude of roughly 8,000 feet. This structural engineering marvel maintains just enough ambient pressure over your internal liquids to prevent that dangerous nitrogen supersaturation. It safely protects you from what the medical world calls decompression sickness.
Section 4. Treating decompression sickness, clinical interventions.
So what happens when that incredible engineering fails, or a deep-sea diver makes a crucial mistake, and those dangerous bubbles actually do form? Well, clinicians use the exact same law of physics to save them. If an aircrew experiences in-flight bubble formation, they follow a strict 3-step physiological protocol. Step 1. Safely reduce altitude, ideally bringing the aircraft all the way back down to sea level. Why? Because descending increases the ambient atmospheric pressure, which physically halts the release of any more gas bubbles from the tissues. Step 2. Administer 100% supplemental oxygen. By breathing pure oxygen, we entirely remove nitrogen from the lungs. This creates a massive concentration gradient that literally pulls the dangerous dissolved nitrogen out of the blood and tissues so it can be safely exhaled. And Step 3. Prioritize landing immediately for a comprehensive medical evaluation by a trained flight surgeon just to assess for any lingering tissue damage. Now, if a patient's symptoms are severe, we're talking crippling joint pain or alarming neurological deficits where bubbles are blocking blood flow to the brain, they are rushed to hyperbaric oxygen therapy. A hyperbaric chamber essentially functions as a reverse time machine for our soda bottle analogy. We place the patient inside the sealed chamber and significantly increase the ambient pressure surrounding their entire body. Returning directly to Henry's law, as we increase that external pressure, the stubborn gas bubbles that have already formed in their tissues and blood vessels are physically forced to dissolve right back into the liquid bloodstream. This completely eliminates the blockages. We are quite literally repressurizing the patient, just like putting the cap tightly back onto a carbonated drink to stop it from fizzing.
The crucial takeaway here is that managing decompression sickness is never a one-person job. It requires a highly coordinated interprofessional medical team, all operating on a deeply shared understanding of this fundamental physical law. Nurses are right there on the front lines, expertly assessing for sudden neurological changes or severe joint pain, which are the classic clinical signs of bubbles blocking critical blood flow. Advanced practitioners step in rapidly to administer that high-flow oxygen and coordinate complex emergency transfers to specialized hyperbaric facilities. And pharmacists play a really vital, often behind-the-scenes role, ensuring the correct adjunct medications are immediately available to manage pain or inflammation, while meticulously checking for adverse drug interactions that might be altered by extreme hyperbaric environments. It is applied physics, but executed flawlessly as a team sport.
Section 5. Temperature and other variables. Beyond the basics.
For those of you who love the deeper science, let's look at how Henry's law shifts when we change the environmental variables. We've talked extensively about pressure, but the specific chemical nature of the gas matters incredibly. Notice the solubility constant for carbon dioxide at the very bottom of the data here. These constants measure how many moles of a gas dissolve per liter of water per atmosphere of pressure at standard room temperature. Carbon dioxide's constant is 3.4 times 10 to the negative 2. Compare that to nitrogen just above it, which has a significantly smaller constant of 6.1 times 10 to the negative 4. This mathematically proves that carbon dioxide dissolves vastly more easily into water than oxygen or nitrogen ever could. And this is exactly why carbon dioxide is the universal gas of choice for creating fizzy beverages. It eagerly packs tightly into the liquid, just waiting patiently to be released.
And, of course, we absolutely cannot ignore temperature. The Van Hoff equation models the temperature dependence of equilibrium constants. In clear practical terms, for most permanent gases dissolving in water, as the ambient temperature goes up, the gas solubility goes down. Heating a liquid adds kinetic energy, which actively forces dissolved gas molecules to break their bonds and escape the solution. This is exactly why a warm carbonated beverage left out in the sun goes flat so much faster than an ice-cold one kept in the fridge. The thermal energy physically alters the Henry's law constant, driving the gas out of the solution long before you even get to take a sip.
So, as we wrap up this explainer, I want to leave you with this lingering thought. How incredible is it that a seemingly simple physical relationship, jotted down by a physician over 2 centuries ago in 1803, completely governs everything from your casual afternoon refreshment to the dark, crushing depths of the Mariana Trench to the pressurized, highly engineered cabin of a modern jetliner? Henry's Law is a beautiful, powerful reminder that the universe operates on fundamental, unbreakable rules that scale across literally all environments. The next time you open a sparkling beverage and hear that deeply satisfying hiss, I really hope you'll take a brief moment to appreciate the incredible, life-saving physics leaping right out of the bottle. Thank you so much for joining me to explore this topic. Keep learning and keep looking for the magnificent science hidden right in plain sight.